So good morning. Today we're going to continue with FET and MOSFET if possible at the end, but that might be a little ambitious. So let's see. Um, might go at a little faster pace than usual, but we still have time to answer questions. Okay. All right. So just as a quick recap, we were looking at a N-channel FET that was implanted with a P-type material on both sides of the channel. By normal interaction at equilibrium between the P and N junction, we have a depletion region that is established at both ends. Both of the P-type materials are connected together into one single terminal known as the gate, and the far ends of the channel are labeled as the drain and the source. Okay, we saw we looked at the case where the drain is grounded, meaning VDS is 0 right here. And then the channel, at this point, the channel is open. And if we apply a negative voltage, a negative bias at VGS at the gate with respect to the source, right here, then the channel starts to close because the depletion region is widening because the PN junctions are in reverse bias. Okay, so drain is grounded, VDS is equal to 0. VDS is equal to 0. We apply a increasingly negative voltage at the gate. The depletion region increases. At some point, both of the depletion regions meet up, and then we say the channel is blocked off or the channel is pinched off. Okay, so that is one case where the channel is pinched off. Now let's look at what happens when VGS is 0 and we apply a bias at the drain. Okay, so if VGS is equal to 0 right here, and the channel is open at this point, we apply a voltage between the drain and the source. Oh, electrons are attracted and current flow results. Okay, so there's movement of charge carriers. It's an N channel, meaning there are free electrons available to conduct charge. When you apply a positive bias, electrons are attracted. Current starts flowing through the device, through the channel. Okay. You guys with me so far? Right? Channel is open. You're applying a positive bias. Electrons are attracted. Currents flowing through the channel. But what happens here? It's an N channel, right? So let me just draw another illustration right here. This is N-type material, and you have P-type material here. And you apply a positive bias here versus the source right there. So applying a positive voltage to an N-type material, what happens at the junction, the PN junctions? Right? Chapter 2. Reverse bias. If it gets reverse bias, depletion region increases. So this is the case where VGS is not being applied. VGS is at 0. Okay. In the previous case, VDS was 0 and we were decreasing or we're increasing the negative voltage at VGS. Now VGS is at 0. You're increasing the positive voltage at the drain. VDS is increasing positively. The effect is still the same. The depletion region is still increasing because of the reverse bias. And at some point, both ends are going to come up and meet together. So we have current flow, but increasingly the channel is increasingly being constricted, and at some point is going to get pinched off. So for both cases, VGS as well as VDS, the pinch off occurs. Okay, but technically the pinch off voltage that is referred to, VP, is for this scenario when VGS is equal to 0. So there is a pinch off voltage for every VGS level. Okay. Right now, VGS is 0. VDS is increasing. Channel gets pinched off, which is illustrated right here. That's the point where the channel first meets. Okay. So again, pinch off will occur when VDS is 0 and also when VGS is equal to 0. Okay. All right. So far, so good? Yes. So yeah, the drain and the source are exactly the same. And theoretical construction of an FET is symmetrical. So both can be interchanged. Drain can become the source and source can become the drain. But again, depending on the application, there are differences in manufacturing. So it's not always exactly the same in all FETs.
We find like forward current as from source to drain.
Drain to source, IDS. Yeah. Forward, yes. So with regards, so the question being asked is, which directions are we taking for the current and by extension for the voltages? So voltages are always measured as gate to source and drain to source. Current is also measured always as drain to source. So we have VGS, and I believe I did note that, yeah, here. So last class I noted, we always take the voltage VGS, meaning the positive reference is at the gate, negative is at the source. And hence we say VGS is negative. Obviously, going back to circuits 1, VGS is the same as VSG, except with a minus sign, right? So if you apply a negative voltage at VGS, it means it's positive voltage at VSG. Okay. So let's talk a little bit about the device physics. So we have a semiconductor material. We implant our dopants in there. We create an N-type material. Okay. So that N-type material, because of the dopants, inherently has resistance, or sorry, resistivity. Okay. So when we create this channel between the two PN junctions, between the two gate junctions, the channel that is established has some resistance. And that resistance is known as the channel resistance RCH. RCH. So, and because of the device construction and the device physics, we say the channel has some resistance, is known as RCH. And like all resistances, it uses the exact same standard formula. Resistance R is rho L over A, right? For any piece of material, if you have a wire or a conductor, the resistance of that material is given by the resistivity times the length of that material divided by the cross-sectional area. And so it's the exact same thing for the channel also. So channel resistance, RCH, is given by the resistivity of the channel. The resistivity comes from the fact that we implanted dopant impurities into our channel. Okay. And so that's the material property of that channel, of the manufacturing process. L would be the length of the channel, and then divided by the cross-sectional area of the channel. So for that, let's go. Thought I had a three-dimensional image somewhere. Oh. No, that was different. That was the MOSFET. So maybe I don't in this one. Okay. All right, no worries. You can create one right here. So we have, let's say, this is our channel. So this would be the width, W. This would be the length of the channel. And if you imagine a three-dimensional structure, our implants, we have, let's say, a 500 micron silicon wafer, implant would be just a few microns deep, probably not even a few microns. So then the depth of the implant into the surface of the silicon wafer is the cross, will give us the thickness of the channel, and the thickness multiplied by the width gives us the cross-sectional area. So T times W, the width of the channel, and in this case, T is not the time period, T is the depth of the implant into the channel. Or actually, more appropriately, I should say, the depth of the channel, or depth of implant into the silicon material or into the semiconductor material. And usually it's not very deep. It's a very shallow compared to the actually bulk of the material. Okay. Now, why is this important? So the channel resistance is important because as the depletion region starts to close, the channel resistance increases. And that puts an upper limit on the current that can flow through the channel. Okay. So let's take a pause here. Think over all of this. Let me know if you have questions. Yes. Not quite. So that's going to be the upcoming. It's the next point. Yeah. All right. Any questions? Okay. So we keep referring to the channel being pinched off, right? But it's not quite pinched off. Okay. There is a small gap, so to speak. And through the depletion region, the electrons are able to travel through the channel through the depletion region and cross over to the other side. So the current flow keeps flowing. So if I was to draw a simple characteristic for VGS equal to 0 and increasing VDS and IDS over here, when you first apply, and this is the case where VGS is 0. Okay, VGS is 0 volts. When you first apply a positive bias at VDS, current starts to flow. Okay, current is flowing, so it's increasing. And if you, what do you notice about this current or the shape? Exactly, it's linear, right? Because again, channel resistance, resistor has a linear relationship for voltage and current. So at the initial portion, it is linear. But the channel starts narrowing, both the junctions meet, and when they meet, current does not stop flowing. The discovery was that the current actually saturates. So there is a small gap that is maintained, but the current does not drop. It instead saturates, which means that the electrons are still able to cross through, and the current and the device now behaves like a constant current source. Okay, it behaves like a constant current source. So there's a very high density of electrons and high density of excuse me, a current that flows through there that keeps the current level constant. Okay, and so there is a linear region where the current increases with the increasing voltage, but at one point when the channel pinches off, and again, pinches off would be in quotes because there's still a gap that allows it to flow through, the current is now at a constant level. Okay, and so we have reached the upper limit of the current. And so this is known as the linear region. or to borrow a word from the vacuum tubes, the triode region. Linear region or the triode region where the current increases. And then this is, of course, the pinch-off region on this side. Okay. And here's the one of the most important terms, the value of ID. The value of ID here when VGS is equal to 0 is known as IDSS. It is the drain to source current when VGS is equal to 0 or with the gate source shorted. That's what this S stands for. Short-circuited gate to source. Mathematically or technically, VGS is equal to 0. So IDSS is the drain to source current when the VGS value is equal to 0. And this is the maximum current that the J-FET will allow, or the maximum current that can flow through the J-FET. Okay. And this is highly dependent on the manufacturing process, the device parameters, the length, the width of the device, plus the dopant impurities that are implanted into the device, okay, and the dosage. So it is highly dependent on the manufacturing process. Depending on what application we need or what applications we want to use the J-FET for, then the dimensions and the implants and the parameters would be different. It could run from microamps all the way to 10 amps or so. So from microamps to 10 amps, quite a large variation. Pinch off voltage can run from few volts, from 0 all the way up to like 20, 25 volts or negative 25 volts. That's the range we are talking about for these JFETs. Okay. All right. We're doing good on time. All right, this is a good time to take a pause. Okay. Again, just a recap. First, VDS was 0. We increased VGS negative, increasingly negative VGS. So a channel pinch off. Now we're looking at the case where VGS is 0 and we are applying a positive voltage at the drain and the source. So VDS is positive, and we again see pinch off. Okay. So questions? Yes.
So if I have a JFET in series with circuit and I have a Zener diode in parallel, will I have a current regulator and a voltage regulator?
So the question being asked is if we have a JFET in series, well, I'm assuming the Zener would be in parallel. So Zener diode and JFET would have a current regulator and a voltage regulator. Yes. To be honest, I don't know.
I make a circuit. I have no idea what it does. Should I always put a JFET and a Zener just to make sure it doesn't explode, essentially? The circuit is?
I don't know. Well, Zener, yes. Zener would limit the voltage, yes. But Zener will also have its own current, limit. So power dissipation maximum for the Zener. So it will have a current limit also. JFETs will also have their own limits. So it's not as if it's always going to survive, whatever. Within those limits, yes, it'll work. So again, as I said, every JFET will have a maximum IDSS, and depending on an application, we can choose that. Yeah. But you make a very good point, because the whole purpose of using transistors, FETs, BJTs, MOSFETs, is because we can control it with a third terminal. diode was a two-terminal device. We had straight current flow through there, non-linear, right? But here we can have the two terminals. In this case, it's the drain and the source, and we use a third terminal to control the flow of current or the charge carriers through the device. And that's basically the big key. So yes. All right, other questions? Okay. All right, so this was for VGS is equal to 0. But now let's add both of these together. Okay, we have VDS, we are going VDS positive from 0 to some positive value. But now, instead of 0, let's apply a negative voltage to VGS. What do you think would happen? Yeah, so first case, remember, VDS was 0, and VGS we applied negative. What happened? Right, channel started shortening. So if we look, oh yeah, this one right here, VGS applied 0, channel gap narrows. Next case, VGS was 0 and we increase VDS. But now if we apply VGS negative, the channel is already narrow. The channel is already narrow. So even before we begin applying VDS positive value, the channel is already narrowed. So the maximum current that can flow is already lower. And so if VGS is negative, we'd have something like this. Let's just put a random number on it, but I would say maybe VGS is equal to -1, perhaps. Could be minus 0.5, -1, but something that is slightly higher in magnitude than 0. Okay, and we now again have a different pinch of voltage for increasing VDS. Okay, so VGS is a slightly negative value, so the channel is narrower. That constricts the maximum value of IDS. Then you increase that VGS again, and again increasingly negative value. It's linear region, and then saturates. Linear region and saturates. Saturates, and at some point, obviously when VGS goes to negative, it reaches the point of VP, the pinch off voltage. Okay, so when we join these, we get a region of the Ch4 that is known as the linear region of operation, and everything to the right is the pinch off region. Okay, everything to the left is the linear region of operation. Everything to the right is the pinch off region. And right at the bottom, right here, is what we call as the cutoff region. This is from the first case that we saw, where VDS is 0 and VGS is equal to the most negative voltage that is required to turn off the channel or turn off the device. So cutoff region is VDS is equal to 0 and VGS is equal to VP, the pinch off voltage. The point where VDS pinches off the channel, when it first pinches off the channel, right here, where it first pinches off the channel, that voltage is referred to as VDSP. VDS pinch off. VDSP. And so you'd have a pinch off VDSP value for every value of VGS. And that is what is illustrated on this graph right here. Okay. Those are the pinch off values of VDS for every value, every negative value of VGS. And then there's a graph in the next slide that we can talk about more here. Okay, so we have VGS equals 0 right here at the top. Maximum value of the current, IDSS, that's the maximum value of the current that can flow through the JFET. And for all other values of VGS, in increasingly negative values of VGS, there is a separate right here, right here. There is a separate value, and those values are VDSP, the value of VDS where the channel just about pinches off when the depletion regions first meet. And when we join all of those together, we have a linear region of operation that is towards the left, and then the pinch off region that is towards the right. Okay. And then if we plot, so this is VDS right here. This is VDS, and this is IDS. Okay, IDS. Okay, VDS versus IDS. If we plot IDS levels, or the current drain to source current, for every VGS value, you obtain this transfer characteristic on the left. So you have, this is negative VGS, and this is IDS. Okay, this is IDS. And this is one of the questions on the pre-lab. This is the answer. It asks you to plot the transfer characteristic for the JFET. This is what you need. Okay. All right, let's take a pause. Let me know if you have any questions. Any questions? Okay. So one final thing about this transfer characteristic, the way we plot it is, of course, we take the maximum value of the current from the right and we bring it over to the left. Okay. And that's how we get that plot. Make sense? Right? For every value of VGS, what is the maximum IDS we can obtain? And that's how we get the transfer. Transfer characteristic for any device or any circuit is always showing how the input is being transferred to the output. Okay, in this case, VGS would be the input and IDS would be the output. And so that's why it's known as the transfer characteristic. There's one equation that I'd like to point out, and that is for ID. So ID is given by IDSS. It's drain current equation. 1 minus VGS over VP, the whole square. And IDSS, as I said, comes from the manufacturing process. Is given by Kn over 2 times VP square. Okay. Kn is known as the transconductance factor. And again, that comes from the manufacturing process. Okay. So let's look at an example where we can use a JFET in a circuit, and we are asked to find the Q point or the operating point for the JFET in the circuit. Okay. So typical JFETs are biased with a resistor at the drain, a resistor at the source, and a resistor at the gate. Okay. Positive voltage is being applied between the drain and the source. We are told, or we are given, the values for IDS and VP for the JFET. And the question being asked is, find the Q point of the JFET. Okay, find the Q point. All right, so let's write down what is given to us. 3 resistor values. VDD is the standard nomenclature for a voltage that is applied at the drain, and VGG is the standard term that we use for the voltage that is applied at the gate. Okay. Right now in this circuit, we don't have any separate voltage. In the lab, you will have a very similar circuit, except there'll be 2 power sources, one at the drain, the other one at the gate. Okay. And we'll obtain a set of curves where for every value of VGS that you apply in the lab, and you increase VDS from 0 to a positive value, and then you obtain a set of curves. So right now here, we don't have any source on the gate, which makes our job easier. Okay, so what we want is then we want ID, the drain current. We want VDS, the drain to source voltage. And of course, we also want VGS. Okay. So no matter what kind of circuit it is, if you are doing circuit analysis, it's always the same equations. Ohm's law, KVL, KCL, Thevenin circuit. In this case, we don't need to have any Thevenin equivalent because it's straightforward. We can divide these kind of circuits into an input and the output. The input side would be the gate and the source. The output side would be the drain and the source. So let's first start from the input side. The input side is the gate and source, so we look at VGS. So the input loop is right here. Okay, input loop consists of, actually, let me write it on the right. Input loop consists of 3 voltages. We have the voltage across the gate resistor, then we have the gate to source voltage, and then we have voltage across the source resistor, VRS. Right now, we are not working with currents. We're working with voltages. If you're working with voltages, KVL, right? So we apply KVL. Current is flowing in this direction. So plus minus, you get plus minus, and then plus minus. So all voltages according to this current direction are positive. So we can write KVL expression and obtain VRG plus VGS plus VRS is equal to 0. Then VRG can be written as IG times RG plus VGS plus the source current times source resistance, 0. Okay. Now, here's where it helps with the device physics. The JFET has very high input impedance. So the gate current is almost negligible, almost close to 0. So for many analyses, we can safely assume that IG, the gate current, is equal to 0. And we're going to eliminate variables. So from fundamental principles, we can use Ig value as 0. And because it's 0, remaining expression simply becomes VGS is equal to IS times RS. Okay, IS times RS. No, minus IS times RS. Also, we just looked at the device operation. We have electrons flowing from source to drain, and we have current flowing between source to drain. So what is the relationship between the source current and the drain current? Exactly. They are the same. So the drain current and the source current are the same. IS is equal to ID. So since we need to find ID, we are looking for ways where we can write an expression or an equation for ID. And here we are. Minus ID times RS. Okay, minus ID times RS. So now we have two unknowns. We need to find VGS. We need to find ID. How can we find ID? Well, that is one case, but we don't, again, VDS is also unknown. But we just looked at the equation for ID in the previous slide, so we can use that. ID is given by IDSS times 1 minus VGS over VP. And we are given the values for IDS and VP. Sorry, IDSS, not ID. And so we plug those values in and we obtain 5 milliamps. So it's 0.005. No, and of course, RS times 1 minus VGS is unknown. We leave it as it is, VGS over VP. VP is minus 5 square times RS is 1 kilo ohm, so 1000. Okay. Oh, sorry. ID is IDSS times 1 minus VGS over VP. And so we plug it into that equation. This equation is for VGS. Yes. So now we have a square. So we are going to have a quadratic equation. Don't worry, it's not like the iterative analysis. So we have VGS is equal to 5 times 1. Actually, let's simplify this. We get 5 1 minus VGS of 5, so 25. When we square it, so 5 plus VGS over 5 square. Yeah. No, just 1000. It's times RS. So from here. So RS, that's the value for RS. So we had 5 milliamps. And then RS is 1000, 1 kilo ohm. And so we plug that in. No, we're not doing that. We have this equation right here where VGS is equal to minus ID times RS, right? And ID is given by ID. So I messed up in writing it directly, but IDSS into 1 minus VGS over VP whole square. And you plug this into this equation and you obtain this. And IDSS is 5 milliamps and times RS is 1000. So, all right. So this gives us, what does it give us? 25. And so we take the 25 outside. We get 1 over 5. And then here we get 25 plus 2, 5, 10. 10 times VGS plus VGS square. Okay. Rearrange the terms and you obtain VGS square plus 15 VGS plus 25 is equal to 0. Plug this into your calculators, obtain the roots of this expression, and you obtain two values for VGS. VGS is equal to minus 1.9 volts, or VGS is equal to minus 13.1 volt. Okay, minus 13.1. So take a few seconds and think about which value would be correct. 1.9 or 13. Look at the information that is given to us. Well, it can be greater than 5, actually, because VP is 5 or minus 5 volts. So it can be greater than minus 5 volts. And so, since VP is minus 5 volts, VGS would be equal to minus 1.91 volt. Okay, how much time? Okay, 8 minutes. So now that we have VGS, we can go ahead and calculate the rest of the quantities. We can find ID. ID is the same as IS, and you can find IS from the voltage that is applied across that resistor divided by 1000. So 1.91 milliamps. Then for VDS, we apply KVL at the output. And you apply KVL at the output, we obtain an expression VDD plus VDS plus VRS is equal to 0. Oh, no. VDD is equal to VDS plus VRS plus the drain resistor. And then we can rearrange and plug in the terms. VDD is equal to ID RD plus VDS plus IS times RS. And then therefore, we can write VDS expression as VDD minus IDRD minus ISRS. $12 volts minus 0.00191, 1.91 milliamps times 3000, 2000 plus 1000, just combining both resistors together because the drain and the source current are the same. And so therefore, VDS is equal to 6.27 volts. Okay, 6.27 volts. All right. Still a few minutes left. Okay, write it down. Let me know if you have any questions.
Professor,
Yes.
could you explain again why we assumed IG to be equal to 0?
So where in?
It was in a previous step above. We said IG was equal to 0 and IS
Oh,
became
IG is
equal to
0.
ID.
Yes, the FET has infinite input impedance. Theoretically, in real life, it's very high input impedance. So the gate current is very minimal. It's almost equal to 0. And so we can assume for many cases, for many circuit analyses involving JFETs, we assume IG is equal to 0. And if IG is equal to 0, then the drain and the source currents are exactly the same. And so we assume ID is equal to IS.
Thank you.
All right, questions? So let's see, we have a few minutes. Might talk a little bit about MOSFETs, but before that, announcement quiz is on Monday, as usual, about the material we've covered here. So we've covered JFETs. So I'll assign a short homework and yeah, and a reading assignment about JFETs over the week, over the weekend, starting from today. Then quiz on Monday, and then we'll try to cover MOSFETs on Monday, and then begin BJTs sometime later in that week. Okay. JFET experiment is next week. And so that was my goal. I wanted to finish up JFETs this week. We are doing JFETs next week in the lab. Okay. So MOSFETs. What the heck are MOSFETs? Well, the name comes from, well, the full form is metal oxide semiconductor field effect transistor. That's where it comes from. And similar to the JFETs, we have an N-channel MOSFET and a P-channel MOSFET. If it's N-channel MOSFET, we call it NMOS. If it's a P-channel MOSFET, we call it PMOS. And what if you have both in your circuits? What do you think we call it then? Not quite NPN. It's called complementary MOS, or what you probably are familiar with the term CMOS. And CMOS transistor circuits are basically in every computer chip that we are using nowadays. So CMOS technology is used to build every IC that we use nowadays. Okay. Almost every smartphone CPUs, computer CPUs, all of it is made with CMOS technology. Okay. And this is the beginning of that topic. Anyway, so metal oxide semiconductor. The name comes from the fact that you have a semiconductor, which is right here. Semiconductor. Then you have a insulating material, usually typically created with silicon dioxide. So this is SiO2, silicon dioxide. And then you have a metal gate on top, or gate terminal that is constructed out of some sort of metal. And nowadays, it's not usually metal. Nowadays, that metal is typically polysilicon, heavily doped polysilicon. And polysilicon, of course, is a structure of silicon material. It is not single crystal structure, it is polycrystalline silicon material, hence the name polysilicon. So anyway, it's 9 o'clock. I'll end right here and then we'll pick up here again on Monday. I'll be available in my office. If anyone has questions, please feel free to come by, send me an email, hop on the Zoom. Okay. All right. Have a good weekend and I will see you all on Monday.